In our first video on the topic of linear algebraic equations, we had an introduction of some main concepts, and I showed you an example using some simple geometry. And we also talked about a solution, how to solve a linear system using Gauss elimination. Here we'll talk about introduce matrices and how to describe equations in matrix notation, and how to solve the system using Gauss-Jordan reduction. So the first topic is matrix notation, and we could remember our linear system, our general linear system could be described as in this form. So we have our first equation with the first number on the subscript of A representing the first equation, the second number representing the variable to which it's being multiplied, or the unknown to which it's being multiplied. So that's our first equation. Our second equation was A21x1 plus A22x2 summed all the way to A2nxn is equal to C2 all the way down to A, and remember the mth equation, equation M, as opposed to equation 1, is am1x1 plus am2x2 summed all the way to amnxn is equal to cm. And we could express the same system. We always know we have x1, x2 all the way to xn. So we could, and they always appear in each of these equations. So we could save ourselves a little bit of time in writing all those x's and describing describing the system in a matrix form. And here the row corresponds to the equation. So the first row has 1 in the subscript of the a's. And the columns correspond to the coefficients multiplied by a given variable or unknown. So the row corresponds to the equation number, and each column describes the coefficients associated with one unknown. Right? So for example, the first column are all the coefficients multiplied by x1. The second column are all the coefficients multiplied with x2, and so on. And of course, the right-hand side, this last column is all the terms not multiplied by x, or multiplied by x to the 0 power, if you will. So back to our original system, we had x1, well, the system that we looked at that we solved by Gauss elimination, we had x1 minus x2, we had 3x1 plus 2x2 is equal to 6. Those were our two equations, and we could express that system as 1, that's the coefficient here, and we have a minus 1 here. So we have 1 minus 1, and and the constant term on the right hand side is 1, and then we have a 3 and a 2 and a 6. So we're representing our full system in this matrix notation. Now the objective, so now we've talked about matrices. Now I guess we're moving on to Gauss-Jordan reduction. Now our objective is to solve for x1 and x2, and we did so by transforming the system, again by doing elementary operations into the form of x1 plus 0 is equal to 8/5, and 0 plus x2 is equal to 3/5. Right? That's how we solved our system. And in matrix form, that is 1, 0, and 8/5, and 0, 1, and 3/5. And this form of a matrix is called reduced row echelon. It's a reduced row echelon form. Reduced row echelon form. So what Gauss-Jordan reduction does, and I'll show you in a minute, is to transform any matrix into row or reduced row echelon form. So that's what Gauss-Jordan reduction is about. So now let's define this reduced row echelon. Let's define what we mean by this. And I will go ahead and write the equation or the matrix that we ended with when we solved our first 2x2 system. So the first, there's a series of 4 definitions. So in each row that's not all zeros, the first non-zero element, each number in the matrix is called an element. So in each row that is not all zeros, okay, the first non-zero element is a 1. In other words, it's a leading 1. So you can see that both of these rows are not all zeros, and so for each of them, the very first one or first non-zero element is a 1, right? The 1 is here in the first row, and the 1 is here on the second row. This is a 0 element, and the first non-zero element in the second row is a 1. So that's one characteristic of row echelon. The second characteristic is that in any 2 consecutive rows, and again, not all zeros, the lead one of the lower row is to the right of the lead one of the upper row. So we have two rows, they're not all zero, and they're consecutive. And the lower row has a leading one that's to the right of the leading one in the upper row. The third definition is if a column has a leading zero, leading one, then all other elements in that column are zero. So here is a column with a leading one in it. The other elements in this column are zero. In this case, there's only one other element, and it's in this column. Likewise, for this column with a lead one, the other element is a zero. And then the fourth sort of characteristic of a row echelon form is that all rows made of all zeros are grouped together on the bottom of the matrix. So in this case, we didn't have any rows that were all zeros, but if we did, then we would place all the rows on the bottom, and they'd be grouped together on the bottom. So let's look at an example. So in this example, we're going to have three equations and three unknowns, x1, 2, and 3. And with this system, we'll convert this to a matrix. Again, the matrix is basically just removing the x's, and we're just writing the coefficients on the x's. So we have 1x1, 1x2, and then a minus 1x3, and a 1. That's the first equation. We have a 3, a 1, a 1, and a 9 for the second equation, and then a 1, a minus 1, a 4, and an 8 for the last equation. Now remember, our objective is to write this in reduced row echelon form. And for this 3 by 3 system, we would have 3 rows and 4 columns, the fourth column being the right-hand side. And so our lead one in our first row is on the far left, followed by zeros, and then a constant that's to be determined. And that constant is, this form will give us an x1 is equal to a. And so a is the solution for x1. Our next row, our 1 is going to be indented to the right by 1 column, and we'll get another constant that's yet to be determined, and that'll be the solution for x2. And then in the last row, the lead 1 is indented 2 columns, and the constant that is to be determined is the solution for x3. So this is the form we seek to transform this matrix to. So let's start by eliminating the 3 and 1 from the first column, making those zeros. And we can imagine doing that by, well, there's a number of different ways, but the one I'll choose is, let's take row 2 and can transform that by subtracting 3 times row 1. So if we subtract 3 times row 1, we'll eliminate that 3. And to eliminate this 1 on the third row, let's just subtract row 1. So if we do that, we get our top row just as we originally had it. And we get a 0. A 1 minus 3 is a minus 2. And we have a 1 minus a minus 3 is that, and that's a 4. And a 9 minus 3 is a 6. And for row 3, we're just going to subtract row 1, so we'll get a 0, minus 2. 4 minus minus 1 is 5, and an 8 minus 1 is a 7. Okay, so we've eliminated, well, we've made the bottom 2 columns of row 1 zeros, and now we need to get this lead 1. Let's just divide row 2 by minus 1/2, or multiply by minus 1/2. And let's make this a 0. And to do that, let's take row 3, and I guess we'll take the current form of row 2 and subtract that. So we'll take before we transform row 2, we'll just take the original form of row 2 and subtract that from row 3. And I guess we'll just do that first for consistency, and we'll get 0. 2 minus minus 2 is 0, and then 5 minus 4 is 1, and a 7 minus 6 is 1. And then we'll divide row 2 by minus 1/2. And we're almost there. Well, actually, we've indented our lead 1s successively to the right as we go down the rows. Now we need to make these zeros to get it into row echelon form. So let's start with this minus 2, and let's try to make that a 0. And so we can take row 2 and add 2 times row 3. So we have a minus 2 plus a 2, and a minus 3 plus a 2 is minus 1. And then the bottom row we left the same. So we have now we have C and we have B with now a 0 to the right of the lead 1 in the second row. Now we just have to make these 2 0. And we can start by just subtracting row 2 from row 1. And that will give us a 1, a 0, and a 0 minus a 1 minus 1 minus a 0 is still minus 1. And we have 1 minus a minus 1 is 2. And we have 0, 1, 0, minus 1, 0, 0, 1, 1. And then the last step, we just need to get rid of this minus 1. So let's take row 1 and subtract row 3. Sorry, we have to add row 3, because this is a positive 1 plus a minus 1 will give us a 0. 2 plus a 1 is a 3. And there we have it. We now know that x1 is equal to 3, x2 is equal to minus 1, and x3 is equal to 1. Let's look at another system. x1 plus x2 minus x3 is equal to 1. 3x1 plus x2 plus x3 is equal to 9. And then minus 2x1 minus 2x2 plus 2x3 is equal to minus 2. And this gives the matrix 1, 1, minus 1, 1, 3, 1, 1, 9, and minus 2, plus 2, and minus 2. So again, the steps are to indent each successive row over by one element. So the second row we need to indent by removing this 3. So to the second row, let's transform it by subtracting from it 3 times the first row. And when we do that, we're going to leave our first row the same. And when we subtract 3 times the first row from 3 times 1 minus 3 is 0, we have 1 minus 3 is minus 2. 1 minus minus 3 is 4. And 9 minus 3 is 6. So we've indented the second row over 1. Now let's start to indent our third row over 1. So let's eliminate this minus 2. And here we'll just take row 3 and we'll transform it by subtracting row 1 from it. Sorry, that won't work. We're going to add 2 times row 1. And when we do that, we get a 0, 2 times minus 1 plus 2 is 0, and we have a 0 on the bottom. So here's a situation where we have all zeros on the bottom, and with row echelon form, we're going to keep those zeros on the bottom. We have a lead 1 in the first row, and the first column has with this one has zeros in all the other elements. We now need a lead 1 in the second row. So let's take row 2 and divide by minus 2, or multiply by minus 1/2, same thing. And we'll get our 1, minus 2, and minus 3. And again, our zeros are still on the bottom. So now we have all of the lead ones that we're going to get from this matrix. To complete our reduction to row echelon form, if we look at our second lead 1, we just have to make all the other elements in that column equal to 0. And so that means making this top element 0. And so uh, this is where we start working from bottom up. And so the bottom row is complete, the second row is complete, and now we transform row 1 by subtracting from it row 2. So again, our bottom row is intact. We don't need to do anything to that, as is our second row. And when we subtract row 2 from row 1, we get 1 minus 0. 1 minus 1 is 0. Minus 1 plus 2 is 1. And 1 plus 3 is 4. And so we now have our row echelon form, or reduced row echelon form, and we can start solving our system. So the bottom row tells us that gives us the equation that 0 plus 0 plus 0 equals 0. Our second row tells us that 0 plus x2 minus 2x3 is equal to 0. And the top row tells us that x1 plus 0 plus x3 is equal to 0. Now, this system is a little bit different from the previous system in that we have all zeros on the bottom, which tells us basically that 0 is equal to 0. And that's correct. But in the previous example, the bottom row gave us information about x3. But in this case, we don't have any information about x3. And it turns out that x3 is unconstrained. And it can be anything. And the top two equations tell us that x1 and x2 are functions of x3. That is, if we were to say, let's say x3 is, since it can be anything, let's just say x3 is a parameter called alpha. We'll call this our parameter of our system. And that parameter is represented by alpha. And when we do that, we see that x1 is equal to minus x3, which is minus alpha, and x2 is equal to 2 times our parameter alpha. So we would say this system, it has a solution. And that means it's consistent. Right, by our definition of what consistent means. But it has an infinite number of solutions. And it's based, the number of solutions, or the solutions are based on the infinite values of parameter alpha. And in our situation, well, in this system, we have one parameter that determines the solutions. So this system is has a one parameter family of solutions. So just describing some terminology of how we would describe this system. So as you might recall, any linear system can have three outcomes. It can have a unique solution, and geometrically that would represent the case, well, since we have a three-dimensional system, that would represent the case in which we have three planes, and all three planes intersect at a point. That would be the case with a unique solution. In this case, we have an infinite number of solutions, which would represent the case in which the three planes either intersect in a line, or in which two of the three planes intersect or are coplanar, or well, two or more of the planes are coplanar. This is the second case where we have an infinite number of solutions. We could also get an infinite number of solutions if we had a system that, when reduced to row echelon form, looked something like, well, something like this. Actually, it wouldn't look like that. We would have something in all the columns of the top row, and this tells us that we would have two parameters, because two unknowns are unconstrained. Right, so the bottom rows where we would normally determine x3, but that tells us nothing about x3. Likewise, the second row, which normally tells us about x2, fails to do so. So in this example, x1 would be a function of x2 and x3, where we would set x2 to say be alpha 1 and x3 to be alpha 2, representing our two parameters for our two unconstrained unknowns. So this would have a two parameter family of solutions. This is just another example of a matrix that would represent a two-parameter, a matrix that would represent an infinite number of solutions. So now let's look at the last case of an inconsistent system. Inconsistent, again, meaning no solutions. And the example we'll look at is the equations 3x1 plus 2x2 is equal to 4, and 6x1 plus 4x2 is equal to 0. And when we write that in matrix form, we get a 3, 2, and a 4, and a 6, 4, and a 0. So we now need to indent our second row to the right, and so we'll keep row 1 the same, and we'll take row 2 and transform it by subtracting from it 2 times row 1. So 2 times 3 is 6. Oops, let me write down the first row first. 2 times 3 is 6, and when we subtract that from 6, we get 0. 2 times 2 is 4, and we subtract that, we get 0. And 2 times 4 is 8, and when we subtract that, we get minus 8. And so, and then finally, we need to create our lead 1 from this top row, and we'll just divide row 1 by 3, or multiply by 1/3, and that gives us 1 2/3, and then 4/3, 0 0 minus 8. And we have our lead 1 in our top row, and I guess we could produce a lead 1 in our bottom row just to be consistent with our process here. We would just say, yeah, I guess we would divide the bottom row by minus 8, or multiply by minus 1/8. So let me just squeeze this in here. Row 3, 2 is transformed by multiplying it by minus 1/8. So here is as far as we can go with reduced row echelon form. And the equations that we get is x1 plus 2/3 x2 is equal to 4/3. And the bottom equation tells us that 0 plus 0 is equal to 1. And this is not true. And given that we end up with a false statement, this tells us that our system has no solution. Right? It was inconsistent. Okay, so that I'm going to conclude here. We've this video we looked at converting our system of equations to matrices, and then introducing the concept of reducing our matrix to row echelon form, reduced row echelon form. And we looked at 3 examples. One example in which we had a unique solution, one example in which we had a non-unique solution, and then finally an example in which we had an inconsistent system with no solutions. And so that concludes our discussion of a system of linear algebraic equations.